Welcome back for differential equation, and we shall start today is the chapter 4, and we shall talk about the higher order differential equation. Higher order linear differential equation. Okay, we start with section 4.1. We talk about some general properties. Okay, let's consider the higher order differential. In this chapter, we shall extend the properties of the chapter 3, in fact. So we start with the standard form of nth order differential equation. So P1 of x plus the until, and this is equal to g of x. This is the non-homogeneous equation. Let's call it NH. Okay. Well, these functions are continuous, so we are dealing the same as before. Let's introduce here differential operator Ln, which is equal dn. Before we have L2 here, n equal 2, so here we have nth order, P1 of x dn minus 1 plus bn of x. So your differential equation, the non-homogeneous, is just ln of y equal to g of x. This is the non-homogeneous, the same as the above. The homogeneous equation, when you put g of x equal to 0, so this is the homogeneous equation. So we keep our standard form. This is the standard form so if we have here any coefficient in this term, we need to divide it and we put it in this standard form. So this is the homogeneous equation, differential equation. So it's very easy to write it. Okay, plus Pn of x y equal to 0, the same as the above. It's just we are. So let's deal with ln of y. Okay, definition. What's mean? Okay, we shall talk about the solution now. Y1, as before, here we have not only y2 until yn, linearly independent. So you need to just formulate this equation, if you remember. Call it alpha 1, alpha 2, to alpha n yn equal to 0, and if you prove this equation, these constants are equal zeros, then linearly independent. So the same as before, but we have here alpha n, then linearly independent. Otherwise, it will be linearly dependent. And you know what means that at least one of these is not equal to 0. So let's go now for another page, and we defined the Wronskian before. You remember the Wronskian. For second, we know it. Now for the Wronskian. Here just make the general things for the higher order. So the Wronskian, the value of x. The value, it will be the value of y1, y2 until yn, here in this case. And it's equal, I'll put it here down because there's no space, y1 prime, and you differentiate n minus 1 time. And you repeat here until yn prime, and you differentiate yn n minus 1. So it's more general case. This is the determinant, and this is what we called it before, the value of x. Before we have only y1 and y2 here, nth order differential equation. Okay, another definition for the fundamental set y1. Here you don't have only two solutions, we have n. Fundamental set or fundamental system f. This is linearly independent solutions for the homogeneous equation. We know that before for the H homogeneous equation. So in fact, we just extend here what we mean by the linearly Li, let's put it Li, solution, linear and plus solution. So you need, they must be linearly independent plus solution, and this is what we have before. Let's give a, you remember there is a theorem tell you can formulate a general solution if you have y1 to yn fundamental set, then the general solution for H, which is very important, is just y, before we say C1 y1 plus C2 y2, here we carry on until yn. So this is the most important, the general solution for the homogeneous equation. Okay, now I will introduce Apple identity. If you remember, for second order, here we have it for the higher order theorem, Apple's identity. Okay, identity. What's Apple identity, if you remember? So before we have y1 and y2, here we have y1 until yn solutions for H. Then the Wronskian the value of X means that the value of y1, y2 until yn, we write it like that before, until y1 and y2 equal, and here it will be the value of x0, if you remember, exponential again minus, it will be integral from x0 to x, and you take b1 from your homogeneous equation dt, and this is the formula if you use limits, or you can use very easy formula as we did in the second order, w of x just c exponential just minus, without the limit of the integration, just p1 of x. And if you go back for the last page, p1 is the coefficient of yn minus 1. Okay, so this is will tell us the and finish the what we need here. Okay, I will give you some exercise application for the Apple identity, which is very important, just from the left. Okay, if we go now for the exercise, just a very easy exercise 4.1. I will go for direct for the Wronski. The previous one in the exercise is just you need, maybe it's very quickly you can calculate things about fundamental set. So I will concentrate in the Wronski now, because later on we shall have 4.2, and we shall have the picture completely for how to solve the homogeneous equation. So let's take 4.1.12 and from the book. It's in page 70, I think. Yes, page 70. So page 70 in the book, and we take this exercise. Take this 10th order differential equation. Use Apple identity to solve this. Apple's identity. So we need to use just Apple's identity. Okay, so just write this one in front of you. Very simple, really. Minus p1. Use this without integration. Okay, b1 is the coefficient of 9th derivative, so p1 0 means. See, it's already p1 0. So your Wronski is very simple. Just here 0, so e to the power 0 will be 1, so it will be just a constant. So your Wronski constant, which is mean constant. Okay, this is one. Okay, if you go for number 14, exercise 14, fourth order now. Fourth order. It's here 3 minus y double over I plus y equal to 0. And he gave you a condition, the value of 1 equal to 1. So already your differential equation in the standard form, because 1 here, so your b1 of x is the lowest, this third here, so it will be just 1 over 2x. So use the formula up and integrate. Just put c exponential minus 1 over 2x and here dx. Okay, now we need to integrate. This is very easy. Integral c exponential, and you can just minus half here ln x, and it will be just give you you take the power up and you take it, will be minus, will be cancelled with exponential, so it will be c over root just over x. This is the value of x. In fact, you can use this condition now to find c, so put x equal to 1, it will imply c equal to 1. It will give c equal to 1. So your Wronski, in fact, the value of x is just 1 over square root of x. This is will finish this exercise. Okay, this is will finish this lecture for 4.1, and I hope it will be very later on when we go for 4.2 I will solve more exercise to explain this situation.